If you missed class today, this is what you missed. We learned about linear, bent, trigonal planar, trigonal pyramid, and tetrahedral molecules. I had the class write this entire page except for the stuff in the top left there that says look today's homework page for a link to see these shapes with side-by-side comparison capability, and it requires the KIME add-on. I'm going to show you that right now. You see the molecules, you can pull up any molecules that you like, and what I've done here is I've got a comparison of linear to linear. But if you wanted to see the difference between linear and bent, for instance, when you pick up bent, the bent molecule looks linear until you move it, and for some reason it didn't go. Okay, I got it to go finally, and here you can see now a bent molecule compared to a linear molecule. If you turn this just right, they look exactly the same or very close to. And now as I turn the bent, you can see that you've got the one molecule here, this guy, is coming all over the place, and you can actually compare and see the difference between a bent and a linear. Now we can do another comparison, and for that one I'm going to compare a trigonal planar that looks like that to a trigonal pyramid. And the trigonal pyramid is down here. Here we go, trigonal pyramid. And now you can see the trigonal pyramid and the trigonal plane look pretty close to each other, especially if you move it like this. But as you move this trigonal pyramid, you can see that he is not flat when you look at him sideways. This guy is flat when I look at him sideways. And that gives you the difference between a trigonal plane, okay, which looks like all in one plane when you move him just right, and a trigonal pyramid, which does not look like a plane when you turn him sideways. So there's your trigonal pyramid, and the one that people the comparison that people don't get right a lot of times is the tetrahedral. And here's your tetrahedral, and he's on the left, and now you look at this guy, okay? See, this is different than this guy over here, that when I move him just right, I can get him to look this way and then this way, and he just is not the same as this molecule over here. So this little side-by-side comparison is nice to do, and there's only 5 of the molecules, although there's more in this side-by-side comparison thing. There's only 5 that you have to know for part of this class, or as part of this class. So let's go ahead and continue with the shapes that I did show in class. They were actually a molecular model shape, model pair, or model molecular models, for lack of a better word. And I'm showing here the linear, and these particular models show unshared pairs, which the other model kit, or the other side-by-side comparison online that I showed you, does not have. So, by the way, looking for that model thing side by side, that will be on today's homework page. If you're looking in the top left corner of this slide, the red writing, okay, it requires KIME, the add-on, which you can get at my website. And so that will be under downloads. And let's go on back now, and here we have a difference between shared and unshared pairs. So as I point here, you can see what I'm talking about. The atoms on the outside of this molecule, this guy and this guy, are a different kind of atom than what you see in the middle. In this case, this should represent carbon, and these two guys could be any atom. Okay, they're on the outside. And these atoms have no unshared pairs, so they really couldn't be any atom. They'd have to be hydrogen, because he's the only guy that'll have no unshared pairs. Now, in here you'll see the same unshared pair shape in my molecule kit. And these guys are unshared, these guys are shared. I hope I said that right. Anyway, 1, 2, 3 different shared pairs. These guys are unshared, and these guys have a different shape, you'll see, for their shape as the area in which those molecules, or area in which the electrons travel. And you can see only 2 atoms now. Although these guys look like atoms, they're just unshared pairs of electrons. But this guy is an actual atom in here. And so these are 2 ways to get a linear shape. Now here in the trigonal planar, you can see a trigonal planar thing this way and this way. When you look at him like this, you can't tell whether he's flat or not, but if you look at this, you can see that the trigonal planar is in a plane, and it is actually flat. I call it pancake. But that's the trigonal plane, and you'll notice on that central atom, there's no unshared pairs in this molecule. So this is your second type of molecule, or molecular shape, and now we'll go to a third one. On this slide, first of all, we want to refer to VSEPR, valence, and here we go, VSEPR, valence, shell, electron, pair, repulsion. So for the VSEPR theory, we require you to know that all electrons repel each other. So this pair of electrons pushes away this one, pushes away this one, pushes away this one. One being a pair. I'm talking about a pair here. So each of these pairs pushes each other as far apart as they can possibly get. And that's what determines, and that's what makes actually, the angles that these guys are going to be at. And we'll talk about that more later. But this is the trigonal pyramid. And as we go to the next slide, you're going to see the bent shape. Now bent is represented in this case by water. So water has oxygen in the middle and 2 hydrogens here and here. And here we have the unshared pairs. Now these guys push away the shared pairs as well as each other. And that's why you end up with a molecule that looks bent. And in most molecule sets, you don't see the unshared pairs. So this is kind of nice to be able to see these guys here. And as we go on, our tetrahedral is looking like this. And with the tetrahedron, you have the same shape no matter how you set it down on the table. And if you're looking straight down from the top, you'll see it look like this. And here's your hydrogens, here, 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 and here. And then you've got in the center, which you can only see here, and here you have the actual carbon atom. So these are very, very nice to be able to look at and get a visual on what these shapes are all about. So what we did is had everybody say all of these shapes, the 5 shapes, 2 times. We got together in groups of 4, and everybody said all the shapes 2 times. If they were in a group of 3, they said it 3 times. Now, the last part was using this as a basis for figuring things out, and you should stop the recording right now and write this entire page down, except for the stuff that you see right up there. Okay? This stuff you don't need to write down, but I would write this down for my notes today. And now let's go ahead and look at the Lewis structures that we did in class. These were actual homework problems, and it's important for you to know about the trend for electronegativity. The electronegativity trend is critical to be able to figure out who's in the middle. And let me just draw a red line around this trend box that I drew. Okay, that's the electronegativity. I abbreviated a little bit. And first of all, we did a nitrogen trifluoride molecule, and that is represented by this chemical formula right here. So we then laid out the atoms, and after we laid out the atoms, we put in the bonding electrons here, here, and here. And after adding up the total valence electrons that each of the atoms brings in, 3 fluorines, each bringing in 7, because fluorine is in column 7 on the periodic chart, and therefore has 7 valence electrons. And 3 of those times 7 makes 21. And the nitrogen is in column 5. There's only 1 of those. So our total comes up to 26. We put 2, 4, 6 in the bonds, and we have to subtract that out from the 26. And that gives us our unshared pairs, which I did the dots around the fluorines. And we had 20, so we had 6 unshared pairs on this guy, 6 on this guy, and 6 on this guy. All of them already having the bonding electron, the electron pair that bonded the fluorines to the nitrogens. And then you have an unshared pair up here, and that accounts for 6, 12, 18, 20, and that's our unshared. Now, why is this guy a trigonal pyramid instead of a trigonal plane? Well, let's look. Here's the trigonal pyramid, and the trigonal pyramid has unshared pairs on the central atom. They both have a total of 4 atoms in them. So, having 1, 2, 3, 4 atoms, and having an unshared pair on the central atom, unshared pairs out here on the fluorines don't matter. These unshared pairs don't affect the shape. But the shape is affected by the unshared pairs, which is why I had everybody write this in and this in. So instead of a trigonal plane, we have a trigonal pyramid, and that's because of the unshared pairs. And that's how we get our shape. Going down here to the next example, this was CS2 carbon disulfide, and we started out laying out the molecule, carbon in the middle because he's in column 4 and sulfur is in column 6. And in column 6, the electronegativity will be larger, as we see by the trend up here. The electronegativity increases as we go from left to right. So coming back down here, and we're looking at this guy, carbon in the middle, sulfur on each side. We bond them with the black pairs. Okay, the black lines are 2 electrons each, as are the green, but each line represents 2 electrons. So carbon, column 4, has 4 valence electrons. Sulfur is in column 6 and so has 6 valence electrons times 2 sulfurs, or 2 times 6 makes 12. And so we have a total of 16 electrons. Now we're taking out 4 because we have a black line here and a black line here before we put the rest of the unshared pairs in. And these unshared pairs were 12. 2, 4, 6, 8 are left because 2 that were around this sulfur got put into this bond, and 2 that were around this sulfur got put into this bond, making 2 double bonds and leaving carbon disulfide as a straight or linear shape. And why is he linear? Because he has 3. Okay, 3 is the right number for bent or for linear. So as we go back and look at this, we have no unshared pairs on the central atom. Okay, the carbon only has bonding pairs, and he has a total of 8 electrons. So looking back here, we see that the linear has no unshared pairs on the central atom. And I forgot to put the L in there, so let's put that in. This is central, and our thing has moved, so we're going to hold for a moment. And now we can see that I have this spelled correctly, central. No unshared pairs on the central atom makes it linear. If it has shared pairs, it will be bent. And same thing with trigonal planar and trigonal pyramidal. Unshared pairs on the central atom for a trigonal pyramid make it a trigonal pyramid instead of a trigonal plane. And so that's how we determine that guy. Now let's go on to our third one. We only got to this in one of the periods today, but everybody's going to get the benefit from it if they watch my video. So let's go ahead and complete this guy. We got boron in the middle, and we got hydrogen out here. Now, the reason boron's in the middle of this guy is not because of electronegativity, but because of hydrogen. It can only be in the outside because he can only take a maximum of 2 electrons, and that makes him stable, and more electrons would make him unstable. So anyway, let's put this guy together. Okay, these are bonding pairs that I just put in, and so now we have put in a total of 6 electrons. Let's see how many total we have. Boron is in column 3, so he has a total of 3 valence electrons. And hydrogens, we have 3 of those. Hydrogen is in column 1 and so has 1 valence electron. 1 times the 3 hydrogens. Here we go. See, we have 3 hydrogens here. So 1 times the 3 hydrogens would give us a total of 3 valence electrons. So our total altogether is going to be 6. Now, we already have 6 electrons over here. Here, let's get this. 2, 4, 6 that we already put into the molecule just to put them together. So we have to subtract those out. These are bonding electrons. And when we finish with that, we get a total of 0 left, and we finish this molecule. Let's see if everything is correct. Boron is an exception. So boron is sitting here, and he has a total need for 6 electrons, not 8. So he has 2, 4, 6, and he's happy as could be in this molecule. Each hydrogen here, each of the hydrogens is hooked up to 2 electrons, and so they're all happy, and the total electrons in the molecule is 6, so it's happy. Now, if you would like, you can do a little review of how to put things together, and that's something else we did in class, and I'll share that with you now. Otherwise, you can just stop the recording and go on with whatever else you have to do. So before we actually did the stuff that we were just talking about, I started out with this screen, and I showed HCN, hydrocyanide, which would be hydro for, so we have hydrogen and carbon and nitrogen. And so the next thing we have to do is figure out our numbers. So hydrogen brings in 1 valence electron because he's in column 1. Carbon brings in 4 valence electrons because he's in column 4. And nitrogen brings in 5 valence electrons because he's in column 5. So we add them up and we get our total of 10 valence electrons. And so now we're going to go back and do what it says here. We're going to put in the bonding electrons first. So in this particular molecule, we wind up with this guy right here and this guy right here, our bonding electrons to put the molecule together. And to take care of our numbers requirements, we look over here and we see that we have lost 4 electrons, not lost, but we've already put them into the structure. And so our net left to pass out is 6. So let's go on down. We're going to add in the leftovers, and this arrow is pointing at the leftovers over here. So let's go ahead and put those guys in. And as you can see, nitrogen does not have 8. See here, we've got 2, and 2 is 4. Remember, the sticks count for 2 electrons. And they have to be shared. Otherwise, we would write them as dots like you see over here. So we've got 2 bonding electrons here, 2 bonding pairs here and here. That's a total of 4. And unshared pair here, unshared pair here makes carbon have a total of 8. But nitrogen only has the unshared pair and the bonded pair. The total here is 4. So we've got to do some radical things. We've got to make carbon do some sharing. So what we're going to do is come on down and we're going to start sharing. And to do that, let's get this covered so that we just are concentrating on the one thing at a time. So nitrogen still doesn't have enough electrons. Okay, he got an extra pair from the carbon up here, and he's better off because he has now 2, 4, 6, while carbon still has 2 that are unshared, 4, 6, and 8 total. So carbon's still happy as can be, but nitrogen needs more electrons. So more sharing. And as we go over here, we see that we have a hydrogen with 2. We have carbon now with 2, 4, 6, because now instead of having the 2 bonds here, this pair got put into the sharing position, which allowed nitrogen now to have 2, 4, 6, 8. So, as long as we have the right total, the total valence was up here of 10, we have a good molecule. 2, 4, 6, 8, 10, and our molecule is complete, and everything is good. And if you have not remembered this, you want to get down what the exceptions were. And the exceptions are hydrogen, beryllium, and boron, and they're respectively 2, 4, and 6 is what they need in their final molecule. That wraps it up. I hope this brings you back online so far as what you need to know to be able to continue and finish off the homework.